Welcome back to my YouTube channel. Today we will discuss intermediate value theorem for continuous function. Okay. Suppose f is a continuous function from a closed interval ab to r. Okay. Then there exists x1 x2 belongs to closed interval ab such that f of x1 less than equal to f of x less than equal to f of x2 for all x belongs to open interval a closed interval ab. Okay. That means a continuous function is given on a closed interval AB is bounded and attain is LUB or GLB, that is least upper bound and greatest lower bound. In other words, this statement in other words a continuous function f on a closed and bounded interval is bounded and attain its least upper bound and greatest lower bound. Okay. Now start the proof. Let f is a continuous function from closed interval ab to r. Okay. Be a continuous function. Okay. By Weierstrass theorem, Weierstrass theorem, f is bounded. Okay, that is, we know that Weierstrass theorem statement is say that any continuous function on a closed interval ab to r is bounded. Okay, that is the statement. Proof of the Weierstrass theorems already discussed the previous video. Okay. Now, f is bounded. That means the range set of f is bounded. So range set of f attain its supremum and infimum, that is greatest lower bound and least upper bound. Okay. F equal to set of all f of x such that x belongs to a comma b, that is f is a range of the function f. Okay. Is bounded, that is bounded, it is bounded, and least upper bound exists, and let b equal to least upper bound LUB of f. Okay, that is least upper bound of f. We show that there exists x2 belongs to AB such that f of x2 is equal to b. Okay. This is so. We show that there exists x2 belongs to closed interval AB such that f of x2 is equal to b. Okay. This statement is means the function attain its supremum or least upper bound. Okay, that means So suppose this condition is not hold, that is there does not exist any x2 belongs to AB. Suppose this statement is not hold, so there does not exist any x belongs to closed interval AB such that f of x equal to b. Okay, suppose. Okay, so that is for all x belongs to AB, we have f of x not equal to b. Okay, and also here b is a LUB of f. LUB of f equal to f of x such that x belongs to a comma b. Okay, so this implies f of x strictly less than b. Okay, so this implies b minus f of x is greater than 0. Okay, for all x belongs to open interval a comma b. Okay, now let consider h of x equal to 1 by b minus f of x. Okay, for all x belongs to a comma b. Okay, here b minus f of x, this function b minus f of x, this function b minus f of x is continuous on a comma b. So this implies h of x is continuous on closed interval a comma b. Okay, by again Westerner's theorem, hx is bounded. Okay, hx is bounded. So there exists m greater than 0 such that mod of hx less than equal to m. Okay, for all x belongs to closed interval a comma b. Okay, so that is, this implies from defined by h this 1 by b minus f of x modulus values less than m. Okay, this implies minus m less than 1 by b minus x less than m. Okay, so only consider these inequalities. Okay, this part. So this implies 1 by b minus f of x less than m. Okay, so this implies b minus f of x greater than 1 by m. Okay, for all x belongs to closed interval a comma b. Okay, so this implies minus f of x greater than 1 by m minus b. Okay, multiplying both sides by minus 1, so we can find f of x less than b minus 1 by m. Okay, for all x belongs to closed interval a comma b, which is a contradiction. Contradiction. Which is a contradiction? Because B is a LUB of f, that is f of x such that x belongs to closed interval a comma b. Okay. Here b minus 1 by m less than m. Okay, which is a contradiction? Less than b, sorry, less than b. Okay, which is a contradiction? Because b is a least upper bound. Okay. Now, so this contradiction given by this, when we take any x does not belongs to x which has that f of x equal to b, so therefore there exists x2 belongs to closed interval a comma b such that f of x2 equal to b. Okay, that is f of x less than equal to f of x2. Okay, and now next we let b dash equal to get a lower bound of range set of f. Okay, x belongs to closed interval a comma b. Okay, and suppose by similar above, okay, suppose there does not exist any x belongs to closed interval a comma b such that f of x equal to b dash. Okay, that is f of x not equal to b dash for all x belongs to a comma b closed interval. Okay, so and also b dash is my greatest lower bound of the range set of f. Okay, so that is f of x strictly greater than b dash for all x belongs to closed interval a comma b. Okay, so this implies f of x minus b dash strictly greater than 0 for all x belongs to closed interval a comma b. Okay, now we consider g of x. Okay, g of x equal to 1 by f of x minus b dash. Okay, and f of x, this function f of x minus b dash is continuous on closed interval a comma b. Okay, so this implies g of x is continuous on closed interval a comma b. Okay, by again Westerner's theorems, gx is bounded. Okay, so gx is bounded, so there exists m dash greater than 0 such that mod of gx less than equal to m dash. Okay, for all x belongs to closed interval a comma b. Okay, so this implies from here this is modulus value of 1 by f of x minus b dash less than equal to m dash. Okay, so this implies minus m dash less than 1 by f of x minus b dash less than m. Okay, only consider this inequality. Okay, so this implies 1 by f of x minus b dash less than equal to, less than equal to, okay, less than equal to m dash, this is m dash, okay. So this implies f of x minus b dash greater than equal to 1 by m dash, okay. So this implies f of x greater than equal to 1 by m dash plus b dash. For all x belongs to closed interval a comma b. Again by this is a contradiction. Contradiction because my b dash is greatest lower bound of this range set. Okay, so this is a contradiction. Okay, so therefore there exists x1 belongs to closed interval a comma b such that f of x1 must equal to b dash. Okay, so either f of x1 less than equal to f of x, okay, for all x belongs to a comma b. Okay, so therefore this is call it equation number 1 and this is my equation number 2. So from 1 and 2 we have f of x1 less than equal to f of x less than equal to f of x2, okay, and hence the proof.